Hello everyone. Today we are going to start chapter number 10, magnetic field due to electric current. We are going to discuss some of the key points are magnetic force on a wire carrying current, torque on a current loop, moving coil galvanometer, magnetic dipole moment, magnetic potential energy, magnetic field due to a current in a straight long wire, force of attraction between two parallel wires, magnetic field produced by a current in a circular arc of a wire, axial magnetic field produced by a current carrying circular loop, Ampere law and its application. Hence, Christian Oersted has discovered magnetic field when the electric current passes through the wire. Later, Henry, Farad and others shows that magnetic field is an important partner of the electric field. Even Maxwell's theoretical work highlighted the close relationship between electric and magnetic field. This resulted into several practical applications such as electrical motor, generator, computer and communication system. Imagine a current flowing through the wire is held in your right hand. Your thumb points the direction of the current. Curled finger points the direction of the magnetic field. Let's see what is magnetic force. A current carrying conductor is placed in a magnetic field, it experiences a force. It means that the charge when it is placed in a magnetic field, it experiences a force. That force can be written as F vector of is equal to Q into V cross B. V vector cross B vector. Now, as V and B are perpendicular to each other, it is denoted by cross product. When I remove the cross product, I will include sin theta. So the equation becomes Fm vector is equal to Q V B sin theta n cap. N cap is nothing the unit vector, theta is nothing the angle between the V and B. If both electric and magnetic field are present, then the force will be F is equal to Q into E plus V cross B. This equation even can be written as QE plus Q into V cross B. It is also equal to Fe plus Fm. Fe is nothing, force on the charge due to the electric field. Fm is the force on the charge due to magnetic field. This Fe depends on charge as well as strength of the electric field. Fn depends upon charge, velocity of the charge as well as the cross product between the V and B and magnetic field. This equation is called as Lorentz magnetic force. This has an interesting consequence that when charge flowing through with the velocity V is parallel to the magnetic field, then the magnetic field will be 0. If the charge is stationary, V is 0 as well as magnetic field also 0. Consider a force of 1 Newton acting on the charge of 1 coulomb which is moving with a velocity 1 meter per second. Then the magnetic field is defined as V is equal to F by Q V. Its SI unit is Newton second by Coulomb meter. Force SI unit is Newton, charge SI unit is Coulomb, velocity SI unit is meter per second. Dimensionally it can be written as V is equal to F by Q. The SI unit can be written as Tesla T. 1 Tesla is equal to 10 to the power of 4 Gauss. Gauss is not an SI unit, it is a convenient unit. Magnetic force on a wire carrying current. First one, straight wire. Consider a straight wire whose length is taken as L. Apply an external magnetic field perpendicular to this wire, which comes out of the plane of the paper. Let's take I, the current flowing through the wire under the applied potential difference. If Vd is the drift velocity of an conducting electron in the part of the length L. Vd means drift velocity. It is the average velocity attained by the charged particles, that is electron, in a material due to the electric field. Then the charge becomes Q is equal to IT. We know speed is equal to distance by time. So here we can see time is equal to then distance by speed. So here distance is taken as L, speed is nothing, Vd, that is the velocity. So Q is equal to IL by Vd. Velocity and speed are similar, as velocity is speed in a particular direction. Force acting on the charge due to the magnetic field is denoted as Fm. So Fm vector is equal to Q into Vd vector cross B vector. Q value is IL divided by Vd. So the equation is equal to IL divided by Vd, Vd sin theta n cap. As we remove the cross product, I will include sin theta n cap. Consider B, magnetic field and drift velocity as perpendicular to each other, then the angle becomes 90 degree. So the equation comes, that is I, L, B sin 90 degree n cap. N cap is nothing, unit vector. So we know the value of sin 90 degree is 1. Then the equation becomes Fm vector is equal to I, L, B n cap. If the wire is not perpendicular to the magnetic field, then the equation becomes Fm vector is equal to I, L vector cross B vector. L vector is the length vector in the part of the length. Second one, arbitrary shaped wire. Consider a small length dl along the wire. Let I be the current flowing through this wire. We know the force due to the magnetic field in a straight wire is Fm vector is equal to I, L vector cross B vector. Now in this small length, what will be the force? Is equal to D Fm vector, that is equal to I, dl vector cross B vector. Then the force on the total length of the wire is then written as Fm vector is equal to integration of D Fm vector, that is equal to I, that is a constant flowing through the wire, so I have taken it out, integration of dl vector cross B vector. Now B is also uniform through the whole wire, so I can write the equation Fm vector is equal to I, integration of dl vector cross B vector. So I have taken the common terms out. With the help of this equation, we can calculate what is the force due to the magnetic field along this wire. Force on a closed circuit in a magnetic field B vector. We know the force due to the magnetic field along the straight wire or arbitrary wire. The equation was Fm vector is equal to I, L vector cross B vector. Here we are considering it is a closed circuit. Then the equation becomes Fm vector is equal to closed integration of I dl vector cross B vector. The symbol represented is a closed integral. For uniform magnetic field, the equation becomes Fm vector is equal to I in bracket closed integration of dl vector cross B vector. In bracket term, which is closed integration of dl vector, it's nothing, it is the sum of the vector along the closed path. Hence it is 0, the equation becomes Fm vector is equal to 0 as B is uniform. Because the force is due to magnetic field. As the magnetic field is uniform, the force is 0. Torque on a current flow. An electric motor works on the principle, that is magnetic force on a current carrying wire due to the magnetic field. The figure shows that the rectangular coil A, B, C, D is placed in uniform magnetic field. Therefore, the magnetic force will be acting opposite to the segment AB and CD. This results in rotation of the loop about its central axis. The current carrying loop is in the form of rectangular and it is placed in uniform magnetic field, so we can use the right hand rule. It states that the pointing finger denotes the direction of the electric current, middle finger denotes the direction of the magnetic field, and the thumb denotes the direction of the force. As we know, the loop is placed in magnetic field. It's placed in such a way that the segment AB and CD are perpendicular to the magnetic field, but BC and DA are not. So the force acting on the BC will be F4. Let's calculate all the forces. The force acting on the BC will be F4. which is taken as F4 vector is equal to I L2B sine 90 degree minus theta. F2 will be the force which is acting on the side dA, which is equal and opposite to the force F4. So they get cancel each other. The force acting on the side AB and CD will be F1 and F2, which is equal to I L1B sine 90 degree. As we know, sine 90 degree the value is 1. It will be written as I L1B. These are the two forces which are not acting along the same line, so they produce torque. This torque results in the rotation of the loop, so that the loop is perpendicular to the magnetic field. The moment arm is half L2 sin theta above the central axis. So the torque will be torque is equal to I L1B half L2 sin theta plus I L1B half L2 sin theta. When L are half and half, it becomes 1. So the equation becomes I L1 L2B sin theta. If the current carrying loop has n number of turns, then the torque becomes N I L1 L2 B sin theta. Now we know area is equal to length L1 L2, then the equation becomes N I A B sin theta. This equation holds good for all loop irrespective of their shape in uniform magnetic field. Moving coil galvanometer. Current in a circuit or voltage of a battery can be measured in terms of torque exerted by magnetic field on a current carrying wire. The analog voltmeter and ammeter works on this principle. This diagram shows the galvanometer. It consists of coil of n number of turns and mounted in such a way that it is freely suspended about its own axis in radial magnetic field. The soft iron core produces the magnetic field in radial and makes it strong. It is placed in between two poles of Gauss magnetic field. The coil rotates due to the torque present in it has the current flow through it. This torque is NIAB sin theta. If the sin theta value is 1, then the torque will be NIAB. N turns, I current, A area, B magnetic field. This torque is counterbalanced by the torque due to the spring fitted to it. This counter torque balances the magnetic torque and produce deflection. Large current flows, large deflection, as the torque will be large and it gives the value. As we know, the counter torque balances the magnetic torque. Counter torque is known as restoring torque and the magnetic torque is deflecting torque. Deflecting torque is equal to the restoring torque. So, deflecting torque is denoted by the equation that is INAB, which is equal to K, that is the restoring constant, into theta. That's the deflection which is produced. From this I can write even I is equal to K by B and A into theta. This K divided by B and A is constant, so I have written here G, which is galvanometer constant. So the equation becomes I is equal to G theta. If I remove the constant, it becomes I directly proportional to the theta. So as I said, how much large the current is supplied, that much large I will get the deflection. Magnetic dipole moment. A current carrying coil can be described in terms of vector, that is mu vector. It is magnetic dipole moment. It is defined as the product of the pole strength and the magnetic length of the magnet. So the equation was mu is equal to NIA. In uniform magnetic field, the torque is calculated as torque is equal to mu B sin theta. Theta is nothing the angle between mu and B. So the equation comes that is torque vector is equal to mu vector cross B vector. If the electric dipole momentum is described by the electric field, then the equation will be torque vector is equal to P vector cross E vector. P vector is electric dipole momentum, E vector is electric field. Here mu vector is magnetic dipole momentum and B vector is magnetic field. Magnetic potential energy. Magnetic dipole is freely suspended in magnetic field, possesses the magnetic potential energy. As we have learned in chapter 8, electrical potential energy is associated with electrical dipole on the account of the orientation in the electric field. As it shows the potential energy of a dipole in the electric field is given by the equation U is equal to minus P vector dot E vector. Analogous to this, the magnetic potential energy of a magnetic dipole in a magnetic field is given by U is equal to minus mu vector dot B vector. As we learned in last standard, cross product sin theta dot product cos theta. So here dot product comes, so the equation comes U is equal to minus mu B cos theta. Theta is the angle between mu and B. Case 1, if theta is 0, then the equation becomes mu is equal to minus mu B cos 0 degree. Cos 0 degree, the value is 1. So the answer becomes, it is equal to minus mu B. It is the minimum potential energy of a magnetic dipole in a magnetic field when they are parallel to each other. If theta is 180 degree, mu, that is U is equal to minus mu B cos 180 degree. Cos 180 degree, the value is minus 1, so the equation becomes mu B. This means that it is maximum potential energy of a magnetic dipole in a magnetic field when they are antiparallel to each other. Magnetic field due to current can be calculated by using the Biot-Savart law. I'll take the arbitrary shaped wire. The current flowing through this wire is taken as I. I'll consider a small element whose length is taken as ds. Then the magnetic field produced by the current can be calculated with the help of this formula, that is dP is equal to mu naught by 4 pi into I ds sin theta divided by r square. We know theta is the angle between ds and r. So I'll multiply and divide it by r in this equation. Then the equation becomes mu naught divided by 4 pi I ds r sin theta divided by r cube. When I remove the sin theta, the equation becomes dB vector, that is equal to mu naught by 4 pi I ds vector cross r vector divided by r cube. Instead of sin theta, I have written cross. This is the equation of magnetic field. Magnetic field due to a current in a straight long wire. Consider a straight long wire whose length is L. The current flowing through this wire is taken as I. We are going to calculate the magnetic field at a point P, which is situated at a perpendicular distance r from the wire. Consider the current length segment, that is IDL, is situated at a distance r from the point P. Then the magnetic field can be calculated with the formula, that is dB cross is equal to mu naught by 4 pi IDL cross sin theta by r square. The magnetic field direction is the cross product, dl vector cross r vector. The magnetic field at the point P can be calculated by all current length segment in upper part of the wire. This can be done by integrating from 0 to infinity. Similar manner, we can calculate the magnetic field intensity at P due to the all length segment in lower part of the term. Both by symmetry, it gives the same value. So we can add both the equation and it becomes B is equal to 2 integration of 0 to infinity dB. When I substitute the value of dB, it becomes 2 mu naught by 4 pi integration of 0 to infinity I dl sin theta by r square. From the figure, by applying the Pythagoras theorem, we can calculate r is equal to square root of L square plus capital R square. We know sin theta can be written as capital R by small r, which is also equal to capital R divided by square root of L square plus capital R square. Then, while substituting in the equation, it comes B is equal to mu naught I divided by 2 pi integration of 0 to infinity capital R dl divided by square root of L square plus capital R square into L square plus capital R square. Then the equation can be even written as mu naught I divided by 2 pi R integration of 0 to infinity dl divided by the square roots can be added up. So here is half and here it's 1. It becomes 3 by 2. Then the equation becomes L square plus R square to the power of 3 by 2. Now, while integrating this part, that is integration of 0 to infinity dl divided by L square plus R square to the power of 3 by 2, it becomes 1 by R square. So when I substitute the integration value, the equation becomes B is equal to mu naught I divided by 2 pi R into 1 by R square. So I'll cancel out the common terms, the equation becomes mu naught I divided by 2 pi R. For the semi-infinite long wire, the equation becomes B is equal to mu naught I divided by 4 pi R. Force of attraction between two parallel wires. Two long straight wires parallelly placed. They are separated by a distance r. Let I1, I2 be the current flowing through these two parallel wires. The magnetic field at the wire 2 due to the current I1 will be B is equal to mu naught I1 by 2 pi r. Using right hand rule, we know that the magnetic field is into the plane. Applying the Lorentz force law, we can calculate the force on the second wire because of the current I2 due to the magnetic field of first wire. Then the equation comes F is equal to I2 delta L, that is the small length I have taken, into B. This equation even can be written as I1 I2 mu naught divided by 2 pi R into delta L. So force per unit length can be written as F divided by delta L, that is equal to mu naught I1 I2 divided by 2 pi R. Let's consider this is the first wire and second wire. Current flowing through this wire is taken as I1 I2. Both are separated by a distance r. So let's calculate what is the magnetic field at second wire to the first wire. B1 is equal to mu naught I1 divided by 2 pi r. So force on the second wire due to the current I2 because of the magnetic field of first wire. The equation comes F21 is equal to mu naught I1 divided by 2 pi r I2L sine 90 degree. It's nothing. Both are perpendicular to each other, so it's sine 90 degree. Sine 90 degree, the value is 1. The equation becomes F21 is equal to mu naught I1 I2 into L divided by 2 pi r. Similar manner, we can calculate magnetic field on first wire due to the second wire, that is B2 is equal to mu naught I2 divided by 2 pi r. This is out of phase, so here written as dot product, and this is in phase, so it is written as cross product. So the force on first wire due to the current I1 because of the magnetic field of second wire, the equation comes F12 is equal to mu naught I2 divided by 2 pi r I1 L sine 90 degree. Again sine 90 degree value is 1, so the equation comes F12 is equal to mu naught I1 I2 L divided by 2 pi r. As both the values are same, so I can write F12 is equal to F21, that is also equal to F, that is equal to mu naught I1 I2 L divided by 2 pi r. So we want force per unit length, then came written as F by L, that is equal to mu naught I1 I2 divided by 2 pi r. As both the currents are flowing in same direction, the force will be force of attraction. If the currents are flowing in anti-parallel direction, then the force will be at ripple. Magnetic field produced by current in a circular arc of the wire. Let's obtain the magnetic field by one length segment of an arc and then integrate the entire arc of the wire. So, the arc AB suspended at an angle theta at the center O of the circle of which the arc is part of it, and R is the radius of the circle. Apply the bias of Witt law. dB vector is equal to mu naught by 4 pi IDL vector cross R vector divided by R cube. As we know, the DL and R are perpendicular to each other. Then when I remove the cross product, it becomes dB is equal to mu naught by 4 pi I dl R sine 90 degree divided by R cube. We know the sine 90 degree value is 1. Then the equation becomes dB is equal to mu naught by 4 pi I dl by R square. This gives the direction of the magnetic field. Use the right hand rule. Thumb denotes the direction of the current. Align it. Then I'll get the curled finger gives the direction of the magnetic field which is into the plane. So the equation becomes B is equal to integration of dB, that is also equal to mu naught divided by 4 pi I integration of A to B dl by R square. As we know, The displacement, angular displacement can be calculated as ds by r. Then from this I can get dl is equal to r d theta. So the equation comes, this is equal to mu naught by 4 pi I integration of 0 to theta, because that is the limit, r, instead of dl I can write r d theta as from the angular displacement equation, divided by r square. So r and r get cancelled, one r can be taken out. Then d theta, when I will integrate, the equation becomes theta. So the equation comes mu naught I theta divided by 4 pi r. The angle is in radian. This is for the R, A and B. Now I'll calculate the whole arc of the wire. Then the equation becomes B is equal to mu naught divided by 4 pi I divided by R 2 pi. Then it can be even written as B is equal to mu naught I divided by 2R. Common terms get cancelled. The equation becomes B is equal to mu naught I by 2. Axial magnetic field produced by a current carrying circular loop. We can obtain the magnetic field of a current carrying circular loop at different position along its axis. The loop itself in x and y axis with center as its origin O. The radius of the loop is r and a current flowing through this is taken as I. Let's calculate the magnetic field at a point P on the z axis. It is situated at a distance r from the element dl. Apply Biot-Savart law. dV is equal to mu naught by 4 pi I dl vector cross r vector divided by r cube. Apply Pythagoras theorem in this triangle. Then I'll get r square is equal to capital R square plus z square. Then we know dl is perpendicular to r. So dl vector cross r vector even can be written as dl into r, because your dl is in one axis and r is in other axis. So the equation becomes dV is equal to mu naught by 4 pi I dl r divided by r cube. I'll cancel out the common terms. The equation comes mu naught divided by 4 pi I dl by r square. Then by substituting the r square value, the equation comes dV is equal to mu naught by 4 pi I dl divided by z square plus capital R square. From the triangle, we get cos theta is equal to capital R by small r, which is also equal to capital R divided by square root of z square plus r square. Magnetic field at point P on the z-axis can be calculated as integration of dB z-axis, that is equal to mu naught divided by 4 pi I integration of dB cos theta. So dB value is dl divided by z square plus r square. Now we substitute the value of cos theta. The equation comes, that is B is equal to mu naught divided by 4 pi I integration of r dl divided by z square plus r square whole to the power of 3 by 2. That is also equal to mu naught by 4 pi IR divided by z square plus r square whole to the power of 3 by 2. Integration of dl, as it is circular, it comes circumference of the circle, it is 2 pi r. Now cancel out the common term, the equation becomes bz is equal to mu naught by 2 I r square, that is divided by z square plus r square whole to the power of 3 by 2. This is the magnetic field at the point P along the axis z. Magnetic lines for a current loop. As we already know, the magnetic field at a point P on the z-axis, Bz is equal to mu naught I r square divided by 2 into z square plus r square whole to the power of 3 by 2. The magnetic field at the center of the loop, by letting the z is equal to 0 in the above equation, the equation comes B0 is equal to mu naught I divided by 2r. If the coil has n number of turns, the equation comes B is equal to mu naught n I divided by 2r. Consider the point is at large distance, so z is greater than r. Then the equation becomes Bz is equal to mu naught I r square divided by 2z cube. The area of the loop is A is equal to pi r square. When I substitute, the equation becomes Bz is equal to mu naught Ia divided by 2 pi z cube. Ia is nothing, magnetic momentum. So the equation becomes Bz is equal to mu naught m divided by 2 pi z cube. Now multiply and divide by 2. Then the equation becomes Bz vector is equal to mu naught 2m vector divided by 4 pi z cube. It is also analogous to the electrostatistics. So the equation comes E vector is equal to 2p vector divided by 4 pi epsilon naught z cube. Ampere law. It states that The line integral of magnetic field induction around any closed path in free space is equal to the absolute permeability of the free space, that is mu naught, times the total current flowing through the area bounded by the path. So the equations comes, that is B dl into closed integration. Application of Ampere law. Magnetic field due to a straight current carrying wire. A straight current carrying wire, we have considered an Ampere loop of radius r. We have taken an element whose length is dl, where magnetic field is to be determined. B vector dot dl vector is equal to B dl is equal to B r d theta. D theta is nothing, the angular displacement, which can be calculated as dl divided by r. So dl is equal to r d theta. Magnetic field at a distance r from the wire is given by the equation B is equal to mu naught I divided by 2 pi r. So as we apply the Ampere law, that is closed integration of B vector dot dl vector is equal to closed integration of 0 to 2 pi is the integrals mu naught I divided by 2 pi r into r d theta. R get cancelled. When I integrate d theta, it comes 2 pi. So 2 pi also get cancelled. The value remains as mu naught I. Magnetic field of a solenoid. Consider a long, closely wounded helical coil of a conducting wire. The density of the magnetic field along the axis of the solenoid within the solenoid and at a certain distance from the wire is uniform. So, the magnetic field is parallel to the axis of the solenoid. The lines which are wounded white space outside the solenoid and the magnetic field is V. Hence, apply the Ampere law. Closed integration of B vector dot dl vector is equal to mu naught I over the rectangular loop ABCD. The above integral takes the form integration of A to B, B vector dot dl vector plus integration of B to C, B vector dot dl vector plus integration of C to D, B vector dot dl vector plus integration of D to A, B vector dot dl vector, that is equal to mu naught I. The second and third integrals are perpendicular to each other, so they become 0. Third integral is outside the solenoid, so it also becomes 0. Now, hardly left the first one, which when I integrate, integration of dl is L. So, dl is equal to mu naught I. The I is the current flow through the solenoid. So, I is equal to N, number of turns, length, and I, small I is the current. So, we can write BL is equal to mu naught N L I. L get common terms cancelled, so the equation becomes B is equal to mu naught N I. This is the magnetic field of solenoid. Magnetic field of a toroid. Toroid is a solenoid of finite length and bent into the form of hollow circular tube like structure similar to the rubber tube inside the tire of a vehicle. Consider an Ampere loop along the central axis of the toroid. The magnetic field lines are concentrating into the toroid. Apply the Ampere law. Closed integration of B vector dot dl vector is equal to mu naught I, where I is the net current encircled by the loop. Integration of dl becomes 2 pi r. So B 2 pi r is equal to mu naught IL. N is the number of turns in the toroid. Then the equation becomes B is equal to mu naught IN divided by 2 pi r. This is the equation of magnetic field of a toroid. Assignments. Few numericals are given to you. Do it in your classwork. Page number 250, question number 3 to 16. Thank you.